All right, so plan for today is the last class. So basically, before we get to the this problem over here, I want to give you some reminders as usual, do a quick recap, and then we'll dive into the final problem about recursion for this semester. And then I'll do some quick wrap up for the course as well, and that'll be it. We'll see how the time goes. Well, your lab number 5 is due today, midnight. So make sure you don't miss it for the deadline to claim your credits, and I will release the solution tomorrow for you to take a look. And for programming test number 3, I released the result and the feedback yesterday. If you got any concern, questions, drop by. I got my office hour today, 7 p.m. And also, there will be some extra office hour on Thursday, 3 to 5 p.m., only for 2030. So if you want to drop by, you're also welcome to. Okay. And also, there will be an exam review session there over Zoom on Friday, 3 p.m. We can say for 1 hour for now, and then if that has to go a little bit beyond that, that's okay too. We'll see, depending on how many questions you have. And on Sunday, I gave a tutorial session on the recursion. We actually solved 3 different problems, and I already put the materials over there as well on the lecture side. Take a look, and then you might find it useful for your recursion learning. All right, so that's the 3 problems that we spoke about, 1, 2, and 3. Okay. And then quick recap. Okay, before that, any question about the course? Yeah. Yeah, for sure. I'll do that. Since it's due midnight today, I might do that maybe slightly after lunchtime tomorrow. I'll do that. Yes, for sure. Yeah, of course, you can go over the solution. If you want to talk to me about a solution, drop by on Thursday and we'll talk, okay, about lab number 5. Or any questions related to abstract classes or interfaces or anything else that's covering the exam. All right, so from last Thursday, the only thing I want to draw your attention to would be, and of course, let me just give me a moment. We spoke about the last recursion problem on the string occurrences of, right? You can take a look. Not much to say. You can also watch out the recording if you want to recall the detail. The most important thing to recall from Thursday will be whenever we want to call a recursion on array, which we're going to use again for today's problem, okay? And the very inefficient way to do it is by creating some subarray, which is going to be number 1, wasting the spaces at all the levels of intermediate recursive call. And also, every time you create a subarray, you're going to waste the time to actually run the loop to really copy over the content from the bigger array to make the strictly smaller array. And as we'll learn in the follow-up course to this, 2101, we're going to see that the running time for this particular solution here is pretty bad. All right, so that's why we're not adopting that. What we do instead is we are taking advantage of the call by value property over here. So rather than creating subarray in each level, we simply pass by value or call by value the address of the array. And then every time we simply change the indices specifying some range. So we start with, for example, 0, 2, which will cover the entire array, and then reduce that into 1, 2, which would be a strictly smaller array, and etc. So we can still reach the base case where the range of the element to look at will be either 1 or 0. That will be the base case. So that's the most important pattern that we learned from Thursday. And you will see that many problems that we discuss afterwards were based on this pattern, even including what I said in the tutorial session on Sunday, and also what we're going to do today as well. They're all consistent. Good. All right, so we talk about all positive, and just to remind you, so we talk about either for all or exist. You should really watch out for the base cases, either return true or false. All right, just make sure you understand when to return which. All right, and that's about from last Thursday. There we go. Okay. All right, any questions from last Thursday you want me to clarify? All right, that's good. Let's now talk about the Tower of Hanoi. Okay, it's an interesting puzzle and very nice one to really solve together. Quite a complicated one, but I think hopefully with some guidance from today's lecture, I don't really expect 100% comprehension. It's not even for me when I learn about the puzzle for the first time, but at least get some understanding and try to spend more time later diving into the puzzle. Okay, good. Let's now go over some background. And I also made the Java code for Tower of Hanoi available to you, right? So I'll show to you how you can run it. I got both the console tester version and also the JUnit tester version, right? You can try both. All right, let's now take a look at the slides, and then we'll go over that. All right, so that's the basic shape of the puzzle. Let's now go over some rules, and then I'll show you some demo on how to play with it. All right, so here. All right, so that's the largest scale problem. Of course, here we say 8. If you count the number of disks on one of the pack over here, we got 3 packs, 1 pack, 2nd pack, and 3rd pack. So the idea is we start with a single pack with all the disks going from the smallest down to the largest, right? And in this particular problem here, we got 8, all right? So what's the goal? The goal is you want to move one disk at a time, which I'll show to you, and then you never move a larger disk onto a smaller one. That's the rule. You can never violate it. And then eventually you want to move all the disks from one pack to another one. All right, so that's the problem for Tower of Hanoi. Let's see some quick demo right away. Okay. All right, so let's see. We have here. So I'm going to tell you how to do with a single disk. That will be the base case, obviously. And also 2 disks, which will be already too big for us to solve. And then we're going to take a look at another more complicated one with 3 disks. Okay. Well, with only 1 disk, let's say we want to move from pack 1 to pack 3. Easy. Base case, you simply move it to there. Base case. Easy to solve right away. You don't need any recursion. For this one here, let's say we got 2 disks, right? You can see we got a smaller one, we got a larger one at the bottom there, right? What you can do is, you can see we want to move conceptually from P1 to P3. That's what we want to do. There is an important concept I want to identify right away, which we will see computationally in the Java code. When I say I want to move from P1 to P3, that means the remaining pack over here is what I call intermediate. The intermediate one is going to be very useful when we got a very large problem to solve. All right? I'm going to identify that right away. So P2 over here is so-called intermediate pack. All right, so in this case, the idea will be I can move this one here to the intermediate. And then, of course, I cannot stack this on top. That'll be violating the rule. I cannot do that. I can now maybe move this to P3 over here, and then now I can move that from the intermediate back to where I want to. Like that. Well, you can see these two are pretty easy cases, right? You can see them right away. And now, the more complicated one will be this one over here. This one, apparently you got 1, 2, 3, as opposed to 2. Still too large to solve right away. So let's now try to solve it first. How about that? So what I can try to do is, let's try this. I will move maybe this one here, and this one here. All right? And then maybe I can do this one here. Now I'm almost done. Somehow I'm more like a halfway, because now I have successfully moved this guy over here at the bottom into the destination, because I want to go from P1 to P3. And then this guy over here, which is in itself a tower, like a strictly smaller tower. Somehow I successfully moved that to the intermediate pack. I want to go from P1 to P3, but I just moved that to P2 temporarily. So the second half will be, I can maybe try to do this one here, and this one here. Oops, sorry. A bit tricky. All right, that's a solution. All right. Of course, you can try it out yourself too. You might have other solution. The way I'm trying to solve it, which I'm going to explain to you, I really follow some very systematic strategy to make sure I always have a unique solution to the problem. However, I want to give you at the end of today some flavor about 2101. Whenever you design some algorithm, not only that you want to make sure it's correct, of course, correctness is priority. If it's not correct, useless. Once we are sure it's correct, how efficient is that? That's also something we want to do a little bit analysis today at the end. All right, so before I talk about the detailed rationale of this particular one, let's add some mystery to this puzzle here. Not too sure if you guys heard about it. All right, so I'll just show you on the slides over here. Okay, I got this one from Wikipedia. So I heard about this legend here. You maybe have heard about that as well. For those of you who might be familiar with more about Indian culture, you can explain to us what that really is. But I got very superficial understanding. Forgive me. So some people working in the temple in India somewhere, they try to carry out the so-called sacred tower of Brahma. Basically, they're gonna follow the Tower of Hanoi rule. But now the only difference is, rather than 8, they got 64 discs, much taller. And they basically have started this movement since a long time ago, maybe about 1,000 years ago, or even earlier. The idea would be they want to try to eventually move from all the 64 discs from one pack into another. I just show you 3. Doesn't seem to be too bad, right? And 64, maybe it's not going to take too much longer. And here is the legend. They said, according to the rule, once it's completed, they said it will be the end of the world. That's according to the legend. But today, we're actually going to see, number 1, how we can solve it, just like people working in that temple is going to solve it. Number 2, we're going to try to predict exactly how long it's going to take them to really solve the puzzle before the end of the world comes, right? According to the legend. That's something we're going to see. All right, so this slide here is just to give you some, like a side story about this. So what we'll do now is we're going to go back to the problem there and start with something small, okay? So let's now go over the strategy, okay? So doesn't matter how many discs you're given. You might be given 1, might be given 2, maybe given 8, doesn't matter. So here will be the strategy that's going to be applicable to all the cases. 3 stages. Okay. Stage number 1, somehow let's say you're given n discs. You're going to divide that into a strictly smaller problem with n minus 1 discs. I'll visualize that in a moment. And somehow you want to move all these, which is a strictly smaller problem, from one pack into some intermediate pack, which kind of show to you intermediate. Okay, that's phase number 1. And step number 1 is already recursive. And then number 2 is going to be some step that can be done right away. And we're going to move the bottom one into the third pack, the destination. And the third step is another recursive step, which is going to move the n-1 disk that used to be on the intermediate pack back to the largest one. All right, so that's kind of the idea. And let me now try to go back to this problem here and give you a little bit more idea. Right, I'm going to go back to my original problem. That's how I started with. Okay, phase number 1. I'm going to divide this particular problem into 2 parts. This part here and this part over here. Basically the bottom one and the remaining part. The remaining part over here is the n-1. Here I got 3 disks, so remaining one will be 3 minus 1, which will be 2. All right. Conceptually, I know that I'm going to move eventually from P1 into P3. So the first phase, I assume I have a solution for you to really move the intermediate one over here from the origin pack into the intermediate one. Of course, it might take some steps to go from there to there, right? Let me say that again. Phase number 1, we're going to take a strictly smaller problem there, which is another instance of Tower of Hanoi. I'm going to conceptually move that into the intermediate pack. Phase number 1. Phase number 2, the bottom one here, I'm going to move that to the destination. Phase number 3, I want to move this one here from the intermediate back to the destination. Itself is just another strictly smaller problem for the Tower of Hanoi. And that one there, I'm just going to move from here back to here. Right? So there are 2 recursive steps over there, which we have to understand conceptually. All right? All right, any questions so far? Right? So that's just some insight into the problem, right? And of course, you can also give it a try. Just print out the page and try to see if you got three disks over here. How would you solve it from the beginning until the end? Right? But I just told you the insight. There are three phases. So I want to give you another quick summary. Right? Looks a bit complicated, but it's not quite. I already spoke about this insight already, but just to make it a little bit cleaner. Okay? We start with this. We want to go from P1 to P3. And then we want to reach the end of phase number 1. The end of phase number 1, we're going to move this strictly smaller subproblem here into the intermediate pack. All right? Once we have done this, we enter phase number 2. For phase number 2, we are going to move the largest one into this destination, which is exactly here. So now we are halfway. Once we got to halfway, we're going to solve another strictly smaller problem for the Tower of Hanoi. And that one there, conceptually, is going to go from this one here into this one here. In that way, ultimately, we can get to this final solution. Right? And every step over here is about how to achieve it. Right? That's something I'm going to trace together with you once we have seen the code in Java. And it doesn't take too many lines of code to really solve this puzzle over here. But you just need to understand how to visualize a recursive solution and see how to trace it. I think that's the most important thing. Okay? And for this one here, maybe revisit again, maybe after we have seen the tracing and maybe some running time analysis. And then you come back for that. All right, any question about this so far, right? About moving from one to another, right? All right, so really three phases. Phase number 1, phase number 2, and also phase number 3. All right, so these are the three phases. All right, let's now look at the Java code. Let's see if there's anything else to say. Before I go over the Java code with you, I'll show you how the program will run. Okay, that's also important to see. Oh, that's the Java code, good. If you download the source code, there's only one class there in the model. It's called the Tower of Hanoi. So this one here is a public method that's going to call the recursive helper method, right? The pattern that we spoke about on Thursday. And then parameters over here for the recursive helper method is quite complicated. It got, let's see, 1, 2, 3, 4, 5 parameters. But that's something I'm going to guide you through about how to do it in a moment, okay? And then you will see some very familiar pattern over here about from larger than 2, from equals 2. So these are the two base cases that we spoke about last Thursday. And then this one here is all the things you need to program. And it will solve the puzzle magically, even if you got 64. So we can even get a solution from 64 and send it to the people working there to let them know how to solve it, right? Anyway, let's see how to run this code. Very easy. So if you click on the file called Tower of Hanoi tester, so that's a console tester version. So over there, I show you 4 different solutions over there, right? 4 different problems. Either we got no disk, in which case we'll pass an empty array. Or maybe we have a single disk, I just call it A. Or we got 2 disks, AB, so we got AB. Or we got 3 disks, or 4 disks, etc. All right? So if you execute the code, it's going to give you the precise solution. Okay, it's going to run. All right. So now in the console, you're going to see, for example, let's say when you have no disk to really move, 0, no steps is needed. When I say I want to move just one disk, it's going to tell you, okay, now move disk A from 1 to 3. And if I got, let's say, AB over here, and it's going to move A from 1 to 2, move B from 1 to 3, and also move A from 2 to 3. Exactly what I illustrated in the very beginning when I first introduced the puzzle. All right? And then you can see it's getting more and more steps involved. Let's say for ABC, you got this many steps, which also correspond to what I just illustrated to you visually on the iPad. And finally, once we are done with today, you can also take a look at what if we got 4 disks. So these are the steps that are necessary to solve the problem. That'll be your challenge, right, to really understand this one here. We wouldn't have the time, unfortunately, for today. All right, I only stick to just 3 disks. All right, play with the code. I think it's already there. It's working. And then you can also see there's an interesting pattern. I showed you how you can also test the console output from system and out the print line. in the JUnit tester. So that's something you can also take advantage of. Okay, I'll leave that to you. Let's go back to the Java code. All right, so we got Tower of Hanoi. So this will be the public method. And as far as the user is concerned, they only pass an array of disks. And we assume, let's say this is a tower. You go from the smallest into the largest. And for the array, we also go from the smallest into the largest. That's our assumption. All right. And then we say we pass the value of the disk. For example, you might have some pointer to the array, pass the value of its address. And initially, we want to go with all the disks. So from 0 all the way to its largest index. From 0 all the way to the largest. And then the helper here, we just simply say 1 and 3. All right? Oh, we'll get there in a moment. But it is more important to see exactly how to see this one here. Okay, let me just make some quick notes. So this part over here is about the range of tower. This will be the range of the array which represents the tower. And this tells you pack number 1. Pack number 1. This one tells you it's pack number 3. Initially, we want to, let's say this particular tower over here is going to be stored in the array A, B, C, D, E, etc. And then we say we want to solve the entire tower. So that's why we go from 0 to the largest index. We want to move them from pack number 1 all the way to pack number 3. And we assume that for these two values over here, it only can be either 1 or 2 or 3, we assume. All right? All right, so far so good, I hope. And most importantly, we got to understand the helper over here. So this is the recursive helper method for the Tower of Hanoi. All right? And let's now go over one by one, and I'll visualize right away. So this one here is about the call by value, the disks, right? Just the value. We're using the same array. We don't create any sub-array. And then here we got from to to. Oh, let me use a different color. How about that? From to to. So the idea will be, so think about this will be, let's say, from. And also here we got to. Okay? And the from is corresponding to the smallest one. And 2 is corresponding to the largest disk. Right? You can see exactly what we're doing. Of course, there's no easy way to represent this, but I think the simplest one would be just using an array. And here we got origin and destination. Right? Origin here will be 1. That means we go from 1. Destination will be 3 here. That means we want to go from 1 to 3. All right? So think about here. We go from the origin. This is the origin. Give me one moment. Okay. So let's say this pack over here is the origin, and this pack over here is the destination. Okay. Good. And then the base cases. If you got from larger than 2, that means no tower left to be solved. So no steps. And if you got just this one here, this is one of the base cases that tells you from and to is referring to the same element. That means there's only one element or only one disk in the tower. So we can solve it right away. So this one tells you there's only one disk. Only one disk in the tower. In that case, the disk, because from and to are just the same value. Right? I can use the 2 to refer to in the disk. Right? So I can get the actual disk. And then it's going to go from the origin to the destination. Right? As we do the tracing, you'll see exactly how the origin and destination will be used. But this will be the base case. Let's now look at a recursive case. That's the important bit. And the recursive case will correspond to exactly the 3 phases I spoke about over here. Exactly the same. All right? Let's now take a look. There's a little trick over here. Something called intermediate. So here I say intermediate. For example, if I got, let's say I want to go from P1 to P3. I want to go from P1 to P3. Intermediate visually is easy to see. But mathematically, I call this 1, call this 2, call this 3. If I know that I want to go from 1 to 3, how do I get 2? 6 minus 1 minus 3. Okay, let's have another one. Let's say I want to go from P2 to P3, let's say. If I want to go from P2 to P3, apparently the remaining one will be the intermediate one. So P2 to P3, how do I get 1? 6 minus 2 minus 3. I get 1. So that's the formula. It is important to calculate the intermediate. That's where the sub tower should really go into temporarily. That's why we need to calculate that. Okay. So P2 to P3, we got P over here. You got 6 minus 2 minus 3, which will be P1. Right? That's the calculation. As one example. Right? So intermediate over here is very important. Okay. And let's now try to understand the 3 stages, 1, 2, and 3. Okay, we're going to visualize that very quickly for you. And you can see the exact correspondence from the tower itself into the array. And that's how we're going to run the recursion. Okay, so let me call that this 1 here, 2 here, and 3 here. All right, it's going to be stage number 1, number 2, and number 3. Okay, these 3 here. All right. Stage 2 will be the easiest, but we're going to do it in sequence. Okay, stage number 1. Let me start you from this guy here. This is the original problem, which I'm going to make a copy. Okay, right here. All right. So we want to go from origin to destination. And you can see here, we got 1 here, we got 3 here. So that means the intermediate is actually 6 minus 1 minus 3, which will be 2. So intermediate over here is 2. That means the stage number 1, we want to move all the disks from 2 to minus 1. What is that exactly? From 2 to minus 1. Let me show you a different way. So think about this index over here is 2 minus 1, right? And also there is another second last disk from the bottom. That one there is 2 minus 1. All right, you can see in both visualization. And when I say I want to move from and to minus 1, let me highlight that exactly. This one over here basically tells you I want to select the range from 2 to minus 1. This one over here. That one there corresponds to exactly this sub-tower. All right. So what I want to do is I want to move this sub-tower over here from the origin, which is over here, into the intermediate, which is over here. That's what I want to do. That is stage number 1. So after stage number 1, I'm actually going to get something like this. All right, let me say it again. Before stage number 1, I got this large tower for me to solve. And I'm going to divide that into sub-problem over here, basically all the disks except for the bottom one. I'm going to move that thing over there from this into the intermediate. Because I want to go from here to here, the intermediate should be the middle one. So I want to move this sub-tower over here from here to here. That's what I got into here. Okay? All good? Okay. And then we're going to have stage number 2. Stage number 2 tells you you're going, well, this one is easy. I basically want to move the bottom one over here from the origin to the destination. That's what I want to do. All right. Let me also make a copy of that. And then show to you exactly what's going to happen. All right, so that's where we started with. And now I'm going to move this guy over here from here into over here. Okay, let's take a look. So disk 2 over here is exactly the bottom one. All right. So take a look at this one over here is representing the last element in the array over here, and that one there is correspond to the bottom disk at the tower. All right, exactly there. So we want to move there from origin to destination. So from number 1 to number 3, right? That's where we are. Now we're halfway. Okay? Now, stage number 3, conceptually, we want to somehow move this guy here to the very destination. This one was only intermediate. It's only halfway. Okay? So what I will do is I'm going to copy that. Okay, put it there. So what I do is I'm just going to move that from here to there. All right, so these are the 3 phases. You can now see exactly the trace. I start with this. After phase number 1, the sub-problem has been solved to the intermediate pack. After phase number 2, I got this one here and also the bottom here. So now they are ready to be merged in phase number 3. All right. And one final thing to note. If you look at, for example, from to 2 minus 1 over here, right? So that's exactly, again, the same sub-problem over here that we try to look for, right? It's exactly the same again. And that one there is also the same range. That's over here. The reason I try to box that 2 times is because to show to you, we need 2 separate recursive calls, right? In phase number 1 and phase number 3, they're separate. Each one of them is going to take resources from your computer to compute. As we will see, when we try to approximate the running time, you're going to see that that one is very inefficient, even though that's already very systematic. So this one here tells you want to go from intermediate back to the destination. So this one here, go from intermediate to the destination, which will be here. All right. That's about how to understand the Java code. As you can see, Java code itself does not take too many lines to write, but the insight into it is enormous, right? That's why I spend most of the time visualizing what's happening here to you. All right, quick recap before we do some tracing. We got the public method here, and also we got a recursive helper method over here. You want to understand that, number 1, call by value, only one array. We never create any sub-array. And the next 2 parameters, from and to, specify which part of the tower we want to move into the intermediate pack, right? So this is how we visualize in the array. That's the corresponding tower. You can also check out how I did it a few minutes ago. And so these are the 3 phases. You also want to see the correspondence. Okay, I'll let you dive into details, but I think pretty much cover everything. Any question? It's not an easy puzzle. It's not easy. All right, but once you can understand this one completely, I think that can also help you appreciate a bit more about recursive thinking. All right. Okay, now that we got this Java code over here, let's now try to take a look at how we can trace the puzzle. All right. So that'll be the final thing I want to mention before I talk about how efficient the Java code is. All right, tracing. I'll try to do that as complete as possible. All right. I do have the high-level tracing tree in the slide. You can check it out. But I think doing that from scratch with you will be the most maybe that would be the best use of your time. All right. Let's say we have this. Okay. Let's set out the context over here. So we got disks over here. Let's say we got A, B, and C. So we got A, B, and C. A is the smallest one. C is the largest one. Okay. And let's use some color convention over here. Okay. Let's say we got indices. We got 0, 1, and 2. Let's say whenever we talk about index 0, let's use green. Then we're referring to disk A. Okay, 0 here. And also I got blue here. And also I got some orange over here. Okay, I got 3 disks. So think about this is how we start with. This is C. This is B, smaller. And this is A. Okay, so I'm going to write it down for the first time. This is A, this is B, this is C. All right, that's the input. And then this is the original problem. And then according to our strategy, we'll need actually two recursive calls. Somehow we want to move this guy here from here to here. And then move this guy here from here back to here. That's what we're going to see in a moment. All right, we're going to see how to trace it. And the method we're going to trace will be this one here, right? Tower of Hanoi helper. Okay. So I'm going to write it down here. So it will be Tower of Hanoi helper. Okay, I'll start with this. And then in the beginning, we're going to say disks, call by value. And then we want to scan the entire tower, right? That's the whole problem. So it's going to be from 0 to 2. And then we want to move from P1 to P3. In Java, you will simply pass 1 and 3. But for simplicity, for understanding, let me say P1 and P3. So easier for you to see, right? But when you look at the Java code, it's going to be 1 and 3. I'm going to say P1 and also P3. That's the problem we want to solve. So the problem itself tells you that we want to basically move the entire tower, which will be the yellow, right? That will be the entire tower. We want to move it from P1 to P3. Move the whole thing into P3. All right? If you like, I can also say this is P1, P2, and P3. All right? That's how we start with. So now let's apply the strategy the first time. According to the strategy, we're going to need two recursive calls. So for phase number 1, we're going to need a recursive call to Tower of Hanoi helper. Okay, the same address over here, DS. Okay, just the same. And now, how do we get a strictly smaller problem? Strictly smaller problem will be A and B. So that should be index 0 and index 1. All right, so that means we're going to need a strictly smaller range, A and B, which would be 0 and 1. So I'm going to put 0 and 1 over here, and 0 and 1. And then I should really move this one here. Since my ultimate goal is to go from P1 to P3, I should move this strictly smaller tower to the intermediate one. So from P1 to P2. All right? From P1 to P2. That's the first recursive call. And once I have done that, let's say, so what's going to happen is, let me just copy this one here. Okay, so after the first one here, I will be able to move this one here into over here. That's what I'll be able to manage to do. So think about this is the original problem. And this one here is sub-problem number 1. All right, so after this, I should really go for the phase number 2, which we move the bottom one into the destination. Right, that's phase number 2. And that one there, I can just say here, I want to move pack C over here, basically the bottom one. Move C, and then from P1 to P3. All right, P1 to P3. That's phase number 2. So I got phase number 1, I got phase number 2. Right, final phase. I should really move. So after that one there, I should also move this one here. Okay, I'll just show to you quickly. And for phase number 3, we basically just want to move this one here, basically back to P3. All right, so now you got the 2 sub-problems as well. And then I'll finish the tracing. So this will be sub-problem number 2. Okay, problem number 1, this one here, from this into here. Sub-problem number 2, this one here, from here back to over here. All right, that's what we need to do. All right, so now how do I specify phase number 3? All right, I'm going to make another recursive call. And that one there is going to look like something like this. Okay, let me try to make myself some space over here. Okay, that'll be good. So Tower of Hanoi. So Tower of Hanoi helper. Again, I'm gonna do disks, call by value. And then I'm still talking about this strictly smaller problem, which would be A and B, 0 and 1. Think about I'm creating another range over here that's really the same as before. 0, 1 and 0, 1 here as well. So it's going to be 0, 1. And that one there would be, let me use the pink just to be consistent. This one here. And then from where to where? Basically from P2 back to P3. Right? You can see the packs over here is really important for you to see, depending on the phases. And that one there is going to go from P1, P2 to P3. All right. And let's now just talk about, do some quick annotation. So this one over here is the subproblem number 1. And this one over here is simply subproblem number 2. All right. Subproblem number 2, right? And this is an intermediate step. And so these are the 3 phases. Phase number 1, phase number 2, and also phase number 3. And we are not done yet. It's a little bit like a Fibonacci sequence problem. When you want to calculate, for example, let's say, if you recall, if I want to do F4, it's going to be F2 plus F3. But now for F2, I need to get it done first before I can compute F3. Similar. I'm now going to show to you how I can compute this one here, and then it will be your exercise to try to compute this one over here to finish that. Okay, that will be your exercise. Let's now do that quickly. Now, how do I compute this? All right. This is from, this is 2. You can see from is still strictly smaller than 2. So we are not really matching the 2 base cases just yet. Not yet. Okay. So what we should do is we should still divide that into 3 phases. Still. All right. And that one there, I'm going to write vertically. So phase number 1, Tower of Hanoi helper, and then DS. Okay, I'll leave that empty just for now. And then we're going to move something, and also Tower of Hanoi, and then disks. Okay, so these are the 3 different steps. Step number 1, number 2, and number 3. All right. Let's now take a look. So the problem is we want to move these 2 basically from P2 back to P3. Oh, sorry, let me say it again. That's the later one. We start with this. We want to move these 2 from P1 into P2. That's what we want to do. How do we do that? Number 1, we will calculate what's the intermediate. P1 and P2, we know that the intermediate is P3. That means we should really somehow divide this problem here into 2 parts. It's going to be the bottom and also the remaining part. And the bottom one is going to be B, and the top part is going to be A. Right? That's what we're going to see. Okay, I'll write down first, and then I'll show to you. So here we say 0 and 0, and to go from P1 to P3. And then we'll move B, and then P1 to P2. And here it will be 0, 0, and then P3, and then P2. All right, let's now first understand about this part here. So let's say this one here. You can see 0, 0 here, 0, 0 here. So we are really talking about just A. A is really this top part over here, just over here. Or you can think about, we'll start with this. We want to somehow move this one here from P1 to P3. And once I have done that, we can now move B, which will be the middle part, from P1 to P2 over here. And finally, we're going to make another recursive call. In this case, we want to move the top one here that was put here back to here. Okay, so that's something you will have to see, the interpretation. All right. All right, so this will be the base case. This will be another base case. So this is a base case. And this is another base case. And this one here will be move because 0, 0 is referring to A. Move A, P1 to P3. And this one here will also be moving A again. And then you'll be from P3 to P2. All right. So this is important. Okay. We got 1, 2, and 3 steps done already. We got some intermediate step. When you do the exercise for this part over here, right? I'm going to leave that to you. This will be your exercise to try. So if I number 1, 2, 3, this will be number 4. And when you do the exercise, you should really see number 5, 6, and 7. So ultimately, what you will get from Java tracing will be, you got precisely step number 1, 2, 3, 4, 5, 6, 7 to follow to really solve this particular puzzle. Okay? That's what you will also see in the Java code as well. That's also exactly what you will get. 1, 2, 3, intermediate one, and another 1, 2, 3. All right? So that's a correspondence. So all I expect from today, at least for today, will be just see the big picture about how things can be traced. Right? That's something you really want to dive into and really see how P1, P2, and P2, P3, why they are different in this case. It really depends on the strategy. All right? Any question here about this in general? It looks complicated, but think about it's not too bad. We're just following the strategy over here. And the rest will be to translating the idea informally into something very formal, which is Java code. Robert. That's a base case, indeed. Yeah. So the strategy over here, if you think about the second strategy here, the second one here is not a recursive call. It's always a base case itself. Yeah, exactly. Okay, I'll let you study that. And the final bit I want to talk about is this. Yeah, go ahead, Jennifer. No problem. Let's say, for example, here I want to go from P1 to P3. Since I only got 3 packs, if I know this is origin, that's a destination. The remaining one should be intermediate. That's where I'm going to put a sub-tower into temporarily. And the way I calculate is by using some mathematical observation. Because I got 1, 2, and 3, the sum is simply 6. If I know I want to go from 1 to 3, then remaining one should be 6 minus 1 minus 3, I'll get 2. That's how I calculate. So the idea about intermediate for this puzzle here is very important. So that's why we calculate that right in the beginning. Okay? And look at how the intermediate is being used as the temporarily, the destination, and the origin, right? As well. Okay, that's good. All right. What I'm going to talk about now, before that, go ahead. Sorry, say it again. No? Okay, so the solution here is completely general. So let's say this. If I got some arbitrarily tall tower, which can be 8, can be even 64, doesn't matter. So the number of packs over here is always 3, fixed. Yeah, that's the puzzle itself, right? Just the number of this that stack on that form the tower is going to be different. Yeah, but the number of this is going to be only 3. Yes. Maybe that's your question. All right. So what I'm going to describe now, you can also look at the slide. That's a complete tracing. Once you have done the exercise, take a look, right, to match your answer. What I'm talking about now here is not covered in the exam. Because it's a last class, and many of you might be taking again 2101 next term, I want to give you a flavor about part of what we will do in 2101. All right, just for your information. Again, this one here is not going to be covered in the exam. All right. We're going to talk about something called running time. And I'm not going to dive into the formal definition for that. So think about in this way. Let's say we have, not only that we have a systematic strategy, we want to measure how long it's going to take us to really complete a puzzle given n disks. For example, let's make the following assumption. Every time I want to move a disk from one pack to another, let's say it takes exactly 1 second. Pretty reasonable, right? Because I think maybe some of us may take more than 1 second, right? Just say 1 second, just for now, right? And then now we want to know, I want to have a function on the running time. Let's say I got some function called t. And whenever I tell you how many disks I got in the tower to begin with, you can compute to me some number over here that's going to tell me exactly how many seconds it's going to take me to solve the puzzle. For example, let's say in the case of the puzzle in the case of 3 disks, you can calculate, we got 1, 2, 3, 4, 5, 6, 7. I got 7 steps, 7 movement, 7 seconds. All right? So now I want to know in general, if I give you some arbitrarily big number n, how many seconds is it going to take accordingly? All right, so that's the function I'm trying to define. And I will show you some very fun mathematical exercise. Okay, I'm going to do that. And then just as a look ahead for 2101. Okay, first of all, let's now figure out exactly what these two should be. So we got a running time function, t. And we got, for example, base case. If I only got 1 disk, how many seconds? 1 second. Agree? Only move from P1 to P3. Now, what about this one here? That's the tricky bit. For that, I would suggest we take a look at the recursive call. This one here. Also, this one here. And this is the original problem. The original problem there is go from to 2. And from to 2 has n disks. And the running time is t of n, which is exactly how I start from. In order to compute that, I need to solve 2 strictly smaller problems. What will be the size? From to 2 minus 1. If you think about it, look at the tower here. If I want to solve, for example, disk 3, what will be the sub-tower? It will be exactly 2. Basically, n minus 1 minus the bottom one. That's how I get a strictly smaller problem. All right? So what I'll do is, you can think about the time that will take for this one here will be t of n minus 1. So you can see I go from n here down to n minus 1. And also, this one here is also solving another n minus 1 problem. And I also got something in the middle. That one there, as Robert said, that's also a base case, moving just 1 single disk. That one there should be just 1. So this is how I figure out or infer the running time. So it's going to be these two, the same, which will be 2 times t n minus 1 plus 1. So if you ask me how many seconds it will take to complete a puzzle with n disks, I tell you, figure out exactly how long it will take for solving a tower of n minus 1 size, multiplied by 2, plus 1. All right? I haven't done yet. I only formulated the running time. Now what I need to do is to so-called unfold it. Okay? So what I will do is I'm going to copy this one here. So t of n equals 2 times t of n minus 1 plus 1. All right. Now here is a tricky bit. Okay. How do I do this? n minus 1 over here is basically going to be fit in as the new input. So I'm basically going to replace the n over here by n minus 1 and replace every occurrence of n also by n minus 1. That's how I apply the definition. So this one over here will be, so 2 times over here doesn't change. And also I got a plus 1 over here, right? What about this part over here? The t n minus 1 will be itself 2 times t n minus 1 minus 1, n minus 2 plus 1. This is the most critical step to unfold. Let me say that again. I got this equation here as definition for the running time. To really unfold it, I need to keep fitting n minus 1, which is strictly smaller problem, assuming that n minus 1 is still too big for me to solve. I'm going to fit in n minus 1 in place of n. So here n is going to be n minus 1. Minus 1 will be n minus 2. All right, so I'm still applying the definition here. If you don't get this one, that's okay. It's not covering the exam, but you will need to get it next term. All right, which is okay. You still have time. Let's now go for one more unfolding. And then I'm going to show to you some important way to really conclude from there. You cannot just keep unfolding. Otherwise, you're getting nowhere. All right, so let's now do another one here. So I'm going to apply n minus 2 into here. So that will be n minus 2 minus 1, n minus 3. Agree? So what I'll do is I'm going to say 2 times plus 1, 2 times plus 1. And then, so this one here is going to be, again, 2 times. 2 times t n minus 3 plus 1. All right? Now, let's make some observation. One thing you might be able to notice is this. Here I say minus 1. So here I say 1. When I say 1 here, I got 1 turn of multiply and 1 turn of plus. When I say minus 2 over here, I got 2 times 2, 2 terms. I got also 2 turns of plus 1. When I say 3 here, I got 3 turns, 2 to the power 3. And this one here, I got plus 3. For example, here, you can see the 3 here tells me I got exactly here 2 to the power of 3. And here, I got exactly 1 times 3. So magically, well, coincidentally, this 3 here correspond to the exponent and also correspond to the multiplication. That's the observation first. And then, the unfolding, you only got one purpose. You want to unfold for so many times so that you can reach the base case. And the base case is T1. All right? So here's my question for you. Easy. So T of n minus, I know that this part here is something, it will depend, it will tell me how many times I need to unfold. Let me say question mark over here. That will be exactly equal to T1. What should be the question mark over here? n minus something is going to be 1. Anybody? That's an easy math. n minus something is going to be 1. It would be. Okay, if you're thinking, that's good, but I'm going to tell you. Okay, it turns out this one here is going to be n minus 1. Well, I'm pretty sure you can double check, right? n minus 1 is going to be 1. That tells me how many turns do I need? n minus 1 terms in order to unfold all the way down to the base case. All right, so this one here is going to be equal to, so 2 times dot dot dot. I will need exactly 2 to the power of n minus 1. And then ultimately, I'm going to get t of 1. And then I'm going to get plus 1, plus 1, plus 1. And how many turns do I have? n minus 1 turn. Okay, I'm doing that a little bit in a rush, but that's kind of the idea, right, for unfolding. First of all, calculate exactly how many I need here. That's exactly n minus 1 for me to get to 1. And if you look at this, and T1 here is simply just 1. Now, let's now take a look at more. That'll be the conclusion. I know that I need to multiply 2 for so many times. So that's why 2 to the power of minus 1. And this part here is going to be n minus 1. So it's going to be equal to 2 to the power of n minus 1 plus n minus 1. And for those of you who took 1019, you learned about kind of big O, right? Asymptotic upper bound. We know that exponential number is going to dominate asymptotically over linear. So we can ignore this term asymptotically. So what we can conclude is it's going to take about 2 to the power of n seconds to finish a tower of Hanoi with n disks. All right. Again, this page here is not covering the exam. It's only for you to get a flavor about what you will need in terms of mathematical precision for 2101. Seconds to complete n disks. All right. So why are we doing this? Remember that legend I spoke about earlier, about almost 1 hour ago. All right, so that's the Java code. That's the tracing. And that's the running time. That's the unfolding I just spoke to you. And the big O is something that we're going to cover in 2101, not this course. All right, that's a puzzle here. And now let's revisit. Since we know it's going to be 2 to the power of n, and we assume that it's going to take the people working the tempo to move one disk for 1 second. So we're going to need 64 as the opponent. It's going to be 2 to the power 64 seconds for them to complete the puzzle, if they follow through faithfully the strategy. Any idea how long this will take? I'll give you the information. Takes about this much time. So I think we are safe. So we are not approaching the end of the world. It's going to take a long time for them to solve it, if they don't make any mistake in the middle. All right? That's the puzzle. All right? The puzzle itself, you should study, but the running time, you don't need to. All right? That'll be too much for this course. All right, any question about this puzzle here? All right, so we are done completely. You can definitely try the lab I gave to you, and then the notes on the recursion, also tutorial material, etc. Right? Everything. Okay, why don't we take a very short break for 2 minutes, and then I will wrap up the course, and then we're done. It will only take about 5 minutes. All right, take a 2 minutes break. All right, so we are completely done with what's going to be covered in your exam. Let's now just wrap up the course just to see what we have learned, and then that'll be it. If you want to ask me questions at the end, you should be able to, because we got plenty of time left. Okay, there we go. All right, basically the wrap-up slide just showed to you the list of topics that we have learned in this course. I may have missed something, you can remind me, but that's pretty much it. Okay, let's see. We have learned quite a bit, I think. All right, so in terms of the, we also did procedural programming for sure, not just OO. So we have done exceptions. It's not really OO. What in some ways it is, but it's mainly the call stack. That's really procedural programming basics. Catch was specified. That's something I didn't put on the slides. Recursion. As I mentioned before, recursion itself is not really OO, but its thinking is so fundamental. So I think that based from what you have learned in the past 1 week or 10 days about recursion, make sure you study properly, go over all the materials before the exam. I can assure you it's gonna lead you a long way next term when you get to 2101. You're gonna need recursion very badly, okay? Especially when we talk about trees. All right, data structures, not too much, just arrays. And you know what, to be fair, I think you guys also learned about stack, but I didn't really put it here because you only see how the call stack can be used, but I don't really see how we can use that for some useful application, which we'll see in 2101. Okay, mainly just arrays. But in 2101, we're gonna also dive into deeper insight into array. And we're gonna compare array with another foundational data structure called linked list. That's something we have to do as well in 2101. All right, and then, of course, lots of OOP. That's really the main focus for this course. We've done classes, attributes, object, reference, data types. That's basically from Lab 0, Part 1, Part 2 in the review. And we got methods, right? You got all kinds of methods, especially helper method. And for the helper method, we kind of tackle that from two different angles. So in the beginning of the course, we talk about like a helper method for reusing duplicates in your code, so you don't really have your code smell. That's one thing. Another one is so-called recursive helper method, which is helper method for sure, but that one is really has to be separate from the actual method that calls the recursive helper method, right? That's something you want to make sure you also review. Okay, we dot notation, association, basically how we navigate between the classes, context objects, aliasing for sure, and inheritance. We spent quite a bit of time on that. So we started with about how you can reuse the code using the extends keyword and also super keyword, and also single choice principle, cohesion, right? So these are the two design principles. I think that's pretty practical that you guys learn from the course, right? Just don't forget about them. It's going to be useful, beyond this course. Expectation, right? Static type, basically. Substitution rules, right? Review what it is. Static versus dynamic types, and we talk about polymorphism, dynamic binding. So I would say these are the single most two important topics for inheritance, right? And then we talk about polymorphic method parameter. If you're not too sure what I'm talking about, you gotta make sure to review the notes. And also polymorphic collection, polymorphic array. And also polymorphic method return types, which we also spoke about. All right, we'll talk about cast, class cast exception, instance of checks, and also overriding, dynamic binding, especially we talk about equals, right? You want to call the version in the closest ancestor, right? All right, well, we use Eclipse. Of course, Eclipse is not the only IDE there. I'm pretty sure you know how to use IntelliJ for some of you, but the idea is the same. I just want you to remember breakpoint and debugger are really the things you want to rely on whenever you got into trouble. Maybe not system.out the print line to the console, right? It's not going to lead you for a long way. Breakpoint debugger. Unit testing. Regression testing, test-driven development. That's a good practice for you to follow. All right, that's it. The only thing that I didn't really manage to cover, which is okay, that's only, again, a small extension to the inheritance, something called generics. All right? So for those of you who might be interested in studying some additional topics related to inheritance, there's a small lecture there that you can also look at. Okay, I'll leave that to you. And in 2101, you will be given some programming assignments, in which case you're going to learn how to use generics on your own. But I'll give you some learning resources as well. But it's a good thing to learn. All right, beyond this course, two things. This is the book. Usually you guys will buy maybe for 3101, but I think beyond this course, you can also practice about maybe translating from English description about the algorithm or different ways of computation into Java and turn them into JUnit test cases, right? I think that will be some good exercise for you to do. It's not going to be done in just a month. It's going to take a long time. So if you want to invest yourself on some very good persistent exercise, that's one I would definitely recommend. Okay, that's one. Another one that's going to be more relevant to this course about OOP is something called design patterns. We didn't have enough time to really talk about design patterns. Basically, design patterns is about different scenario. You can apply different OO solution. And they are mainly well-known design patterns. For example, if you want to implement a compiler, you will need to know the composite and visitor pattern. That's something we wouldn't cover here. You might be able to learn it maybe in 3311, the software design course. If no, that's something you definitely want to grasp by yourself before you graduate or before your next job interview. Okay. All right, similar exercise. You can get this book here from the library or online, whichever. And then you can definitely try to understand the problem, read the solution. Oh, by the way, the solution they put in the book is C++, not really Java, but it's old language. You can also try to turn that into Java and write some JUnit test cases. All right, for 2101, we're going to assume everything you learn in 2030, and then don't really think what you learn in 1019 or 1090 are useless. They are very useful. Well, once we get to 2101, we're going to rely even more on analysis and logic. All right, and keep practicing Java, and then that'll be it. All right. Now, thank you. Appreciate it. Wow, I haven't heard this for a long time because of COVID. So thank you so much. I appreciate it. All right, guys, any question for me? You can ask me about the exam or anything. Yeah, go ahead. I haven't really finalized yet. How about I can tell you what I have now? But it may not be different because I'm not lying. I'm still finalizing the question. So far, I got 20 multiple choice. And then I got about 10-ish written question. Okay. But it could change on Sunday. So please don't quote me on that. I'm just telling you the truth. But that's what I have right now. So I think for it's going to cover actually quite a wide range of topics. You definitely have to review the OOP stuff. There will be tracing. There will be aliasing and inheritance for sure. There will be some recursive helper method for you to really program, but that one is not that difficult. So just make sure you study what we have covered in the class tutorial. You should be okay. Yeah, so during the exam, I think you'll be kept quite busy because it will be quite a long exam, right? So you just want to make sure, just answer every question to your best ability, and then me and TS will judge. Yeah. Okay, so you wouldn't be asked to really give the intermediate work for your tracing. Okay, that's a good question here. Number one, we only grade your final tracing output if we ask you to trace. Okay, maybe the output should be four lines of output to the console, and what are they? And you should I will try to send you guys maybe the PDF, like a first page of the exam booklet, only the first page about the rules that you have to follow through. So you can read it first before Sunday. So any sketch work you do, please do it on the question booklet, not in the answer booklet. Anything that you put on the question booklet, we're not gonna grade it. Okay. Yeah. No. The difficulty, no. So I'm not lying. The actual exam will be harder. But I think the inheritance part of the example question I gave to you, that will be slightly closer. Especially you will be given like a Java class decorations there, and then number one, you're gonna maybe draw the inheritance hierarchy yourself. From there, you're gonna answer all kinds of questions. For example, well, I can even enumerate now. You have to understand how to understand variable assignments and how the change of dynamic type will go. And if you put a class cast, is it gonna compile? If it is going to compile, are you gonna run into class cast exception, etc. Right? And also a polymorphic array that we spoke about as well. Right? Yeah. You mean like a multiple? Oh, I see. So as far okay, for all the 20 questions I got so far, only single correct answer, no multiple. Yeah. Because I think both me and my TA, we're gonna grade your multiple choice manually. We don't really want to send to the Scantron. Sometimes it might take longer than manually grading it. So for now, only single answer. But if there should be multiple answer, I'll be very explicit about it. Yeah. Yeah. The written question? Well, the written question there, of course, some of them will be like a tracing output. You'll be almost like all or nothing. Maybe we can tolerate for one mistake. If you make one mistake, we can still give you partial marks. But if you maybe trace more than one errors, then we cannot give you any marks for that question. On the other hand, if the question there is more about maybe discussing something or maybe justifying something, then of course we'll try to see how much you show your understanding and give you some partial marks. You mean to write a code? It's possible, yes. So there might be a question there where I think I mentioned that before. I might give you some code fragment. It's almost complete. I say now, I blank out several lines there. Now I want you to fill it out. Of course, what that will involve will be you got to understand exactly what those two fragments are meant to do and try to see what should be filled out in those lines. Yeah. 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 So I think I haven't really finalized this part yet, but there could be several possibility. It could be that we just describe what the problem is, and then I'll say now program from scratch. In which case I gotta rely on the TA to see how close or how consistent your solution is with like a final solution, like a model solution. That's one possibility. Well, maybe I will give you base case, maybe some skeleton, and say you got to follow through that skeleton to program. So that'll be easier for us to create as well. Yeah. Yeah, syntax error. Let's say for example, if you're supposed to call, maybe make a recursive call to m, but somehow you accidentally spell that as m1, and maybe that one's a small one. Maybe we wouldn't be so harsh. We can give you some partial marks, and maybe you're supposed to call maybe method parameters in this particular order, but somehow you get the order wrong. If we don't think that's really too serious, we can also give you partial marks. Missing semicolon is not a big issue, but if you miss semicolon all the way through, maybe we'll deduce some marks, right? You should really put semicolon, right? Just to as if you're programming. Yeah, something like that. Yeah. I can tell you that in some very rare occasion, either we see your solution being so creative or simply so difficult to understand that we might ask the TA to try to maybe translate that into Eclipse to try to see if that's really correct. But we don't normally do that. We'll try to rely on the TA's experience, or maybe I will take a look to see if you're really getting somewhere very close to the solution to get you marks. We don't really run it through a compiler. Normally, we don't. Yeah. All right. 1 minute. All right, thank you guys. Thank you so much. I still got my office hour on Thursday and also review session. And then for those of you who might be taking the engineering sessions again next term, I will see you in January. All right. Thank you so much.